In this video, I will create a new version of egui using the painter struct. Let's start by looking at an example program that demonstrates how the checkbox widget works. We need a struct for the eFrame run native function. The update method includes two checkboxes. The checkbox widget requires a parameter that is a reference to a Boolean variable. Let's run the application. It seems that the checkboxes are not working. Egui is a GUI library that operates in immediate mode, meaning widgets are not stored after being drawn. They are created, displayed, and then removed. Widgets like labels, buttons, and checkboxes do not need IDs. However, containers like window, scroll area, resize, and side panel require IDs to maintain data such as sizes and positions across frames. To retain checkbox states, Boolean variables should be stored outside the draw code. This ensures that the variables persist even after the checkboxes are removed. Let's run the application. Now, we will create real-time plots without using the egui plotting library. Instead, we will utilize the egui painter for our plotting task. Let's proceed with the code. Here are some variable and constant definitions. The red fields indicate the start and end values of the axes. By default, we display 1000 samples on the screen for each channel, with Y values ranging from -10 to 35. The plot data method is in charge of plotting the points on the screen.
In this code snippet, we store data in the variable allData and iterate over all channels. Data from each channel is stored in the variable rowData. We use resize as the canvas for drawing the plot. And the size of the canvas is defined by this field. Resize is a region that can be resized by dragging the bottom right corner. The show method takes a closure that draws the plot. The variable space stores the available space. Actually, space equals the size we set for the resize container. This web page discusses the method available size before wrap. This shows how a painter is allocated for this space. The allocate painter method is explained on another web page. The response struct contains a field called rect. We use the temporary variable full rect to represent the rect field and paint it. We define a closure that maps the data to the screen area. And the clone method is unnecessary. For more details on the remap function, refer to the egui documentation. The closure transforms the data into point positions on the screen, and the points are connected into a line and painted on the screen. Before compiling the source code, we need to modify the cargo.toml file. After making the necessary changes, we can compile and run the program. The issue with this code is that we lack control over individual plots as each plot is created and destroyed for each frame, resulting in no data persistence across frames. To address this issue, we will introduce data memory for each plot.
We have named the improved project Demo4 and added it to the cargo.toml file. Let's start by examining the apprs file. The file begins with use declarations and constant definitions. We are familiar with the hash set when dealing with keyboard events, and brainflow uses a two-dimensional array from ND-array for data storage. We will discuss eplot later. In the apprs file, we have defined a struct called choninfo and implemented the default trait for it. We have also implemented a method for choninfo. This struct is responsible for displaying board info and selecting channel data for plotting. To organize the code better, we will remove this struct from the apprs file and create a standalone file for it. Moving on to the struct myapp, some fields of the struct have been mentioned before. The field pltctx is new, and we will discuss its purpose shortly. The field showChans represents the selected channel indices in 2 dimensions. We will separate choninfo from the apprs file. The field selected_chans has been removed. And the number of selected channels is stored in the field numberChans. The field adjustY will be discussed later. Please pause the video to examine the implementation of the default trait for myapp. 5 methods are implemented for the struct myapp. We have encountered the new method multiple times. The first 3 lines are identical to the previous versions of egui. The 4th line appears similar, but the default function performs different operations. I will explain this shortly. The following 3 lines have been seen before. By default, we choose the EEG channels for plotting. The number of selected channels is stored in the field numberChans. We will skip this line for now. Using the chunks iterator and map function, we organize the selected channel indices into a 2-dimensional form. Let's examine an example to understand how chunks functions. Chunks takes an argument and returns an iterator. If we gather the items of the iterator into a variable s, s is a vector of something. Let's explicitly specify the iterator. And combine these 2 lines into one. We should clarify the type of elements in the vector s as slice references of chars. What if we want s to be a vector of vectors of chars? Compiling the code results in an error. Introducing the map function and the int trait resolves the issue. The int trait facilitates type conversion. Back to our new method, the showChans field is a vector of vectors.
Let's implement the eFrameApp trait for the struct myapp. First, we examine the update method. These 3 lines are the same as in the previous video. Before we draw anything in the central panel, we need to check for resizing. If the window is resized, the size of each plot is calculated. If streaming is stopped, we will display the board info and check boxes for selecting channels to be plotted. I will get back to the code soon. Here, the data is plotted. The x-axes are drawn. I will explain this later. Pause the video to understand how the plot size is updated. The method choosChans is for the interface that allows you to change the selected channels. Our focus is on the plot data method, which arranges the plots in 2 dimensions. As seen in the previous video, we collect raw data. Then we create a plot. We will skip the code for now. Finally, we paint our data. Our question is how the plot is created and how the plot information persists between frames. We will answer this question in the next video.